Our team worked on the Lunar South Pole prospecting mission for our senior design project. We were sponsored by the Arizona Space Grant. Our team consisted of Max Zimmerman, Spencer Petra, Sam Crowley, Lucas Velasco, and Tony Troon. Our team name was Polar Intelligent Navigation Keplerian Functional Lunar Observatory Yonder Device, or Pink Floyd. We competed in NASA's Breakthrough, Innovative, and Game-Changing Idea Challenge with other universities across the nation. We were provided a problem statement to develop a sample lunar payload that can demonstrate systems for exploration, reconnaissance, and science in the permanently shadowed regions, PSRs, in or near a lunar polar region. Here's our virtual design day poster that will be referred to throughout the video. NASA provided us some basic requirements for our design. Our mass had to be kept below 15 kilograms, power consumption had to be kept to 8 watts continuous or 40 watts peak, the bandwidth had to be kept to less than 70 kilobytes per second per kilogram, and radiation had to be kept under 1 kilorad. From our problem statement, we came up with a main objective to design a space vehicle capable of traversing the unknown terrain of a lunar South Pole crater. We then split it into three main objectives. Our primary objective was to design a hopper with a turbine engine, servos, and a microprocessor. Our secondary objective was to verify the hover and impact landing capabilities of our hopper, and our tertiary objective was to simulate the hopper following a trajectory with a vertical landing. For system integration, we will discuss the hopper's components, how they are assembled, and how they work together.
For our components, we have our control moment gyroscope to change the angular momentum of our hopper during mid-hop, our servo package to change our angle of thrust also during mid-hop. We have our engine control unit to regulate the fuel pump and monitor the status of the engine, our fuel filter to get rid of any particles in our fuel. We have our fuel plumb to enable the fuel flow from the tank to the engine. We have our fuel tank, which will contain 10 ounces of kerosene. We have our hopper tank, which will further filter our fuel. We have our inertial measurement unit to monitor the orientation of our body, our microprocessor to communicate with all of our opponents in the system, our batteries, which will be powering all of our components. We'll have 2 of them. And finally, our turbine engine, which will give us our propulsion option.
Here, we can see the exploded view of the hopper. The hopper is made almost entirely of aluminum 6061, and it is assembled with a variety of construction techniques. The outer shell and internal walls are welded together using magnesium filler rods to prevent structural failure. The shell bolts directly onto the base with bolts and self-locking nut plates that are riveted to the shell. This allows us internal access for maintenance of the components. All the internal components have custom-made harnesses that bolt directly to the bottom panel of the shell. We selected the Arduino Mega 2560 microprocessor as the main computer behind this project. It will serve as the controller for the servos and the thrust. It has an operating voltage of 5 volts and a recommended input voltage of 7 to 12 volts. Also, it has 256 kilobytes of flash memory, which is plenty for our needs. It is also small and lightweight enough to fit inside the hopper chamber. The first level functional flow block diagram shows the primary function that the microprocessor will be responsible for. Once the hopper is powered up, the microprocessor will provide electrical power to all main subsystems, then it will stand by for input. The second level details the mobility procedure. First, it will engage the control system, then process and store the input, then execute that command. The command should involve engaging the control system, the fuel system, or the power system, but more likely it will need to do some combination of the three. Here we see the system architecture, which shows the inner workings of the components and how they interact with each other. The battery runs directly to the microprocessor, servos, and engine support system. The microprocessor directly controls only the servos and the engine itself. The hopper has 2 main critical modes, controlling and balancing. The controlling mode is used when the microprocessor is adjusting the servos to create the proper thrust vector. The balancing mode is for correcting the hopper's trajectory mid-hop by receiving input from the inertial measurement unit and making the correct adjustment with the control moment gyro.
Fully assembled, our hopper is 26 centimeters by 26 centimeters by 26 centimeters and has a total mass of 4 kilograms. For our testing, we wanted to determine the maximum allowable impact force the hopper could withstand upon a perpendicular landing with the ground. For this, we used finite element analysis on ANSYS workbench. We quickly discovered that our hopper was over-engineered and it could withstand a much larger force than it would ever experience from hopping with our thruster. We instead tested it from 15 meters, which was a 20% safety margin from the maximum attainable height of 12.4 meters. This visual shows the deformation of our hopper from a 15-meter drop drawn to scale. We found that the maximum deformation was only 12 100,000ths of a millimeter. This visual is of the elastic strain distribution not drawn to scale. We found that the maximum strain was 9.3 times 10 to the negative 7. This visual, also not drawn to scale, is of the stress distribution from the drop. We found that the maximum stress was 60 kilopascals. Here's an animation of the stress distribution of the hopper being dropped from 15 meters up. The final velocity is 17.15 meters per second. Again, this visual is not to scale.
To analyze our propulsion system, we looked at two specific hopping trajectories, a single thrust trajectory and a multiple thrust trajectory. The purpose of the single thrust would be for much shorter hops, because this didn't take into account any angular effects, which is only viable for short hops. While the multiple thrust trajectory, the purpose of the secondary thrust was to readjust the attitude of the rover mid-flight to ensure that our rover would end up landing vertically and not tip over upon landing. Here, we were able to visualize what our multiple thrust trajectory would look like if it were to be performed. The example you're seeing shows an initial burn time of 2 seconds with a maximum height reached of 12.4 meters and a final position of 1.63 meters. From our analysis, we found that a launch angle of 5 degrees was ideal for our situation. We also determined that the secondary thrust angle needed to be larger than the initial thrust angle for our rover to land vertically. For the case you are viewing, the secondary burn occurred at 7 degrees or at 25 degrees when you take into account the rotation of the rover. We were able to determine that the secondary burn would need to last 2.13 seconds to ensure that our rover would land at an angle less than 10 degrees. Our code also allowed us to change this landing angle to make our rover land even more vertical. Overall, we determined the single thrust trajectory was optimal for what we wished to show. It was nice to see that a secondary thrust could be performed if need be and was a viable option, but we thought a smaller hop would be better if we were able to construct our rover. We found a hop performed at a 6-degree angle with a 0.63 second burn time would allow for our rover to travel 0.44 meters, and we believe that this would be a good example to show for design day. We thought this would be a good example due to the low risk and showing that our rover would be capable of hopping.
After testing, we concluded that our hopping method was suitable for mobility and that prototype construction was feasible. Here's a picture of the Pink Floyd design team that put this all together. And we'd like to give a special thanks to everybody that helped us along the way.